Well, as everyone continues to join, I want to first thank everyone. We have a lot of material to cover, so we're going to move pretty quickly. If you do have questions, there's a chat feature that is associated with this event. Feel free to ask your questions there, and we'll try to address them during the FAQ. We'll also follow up if there's anything in more detail that we can provide for you. We have a great event today with our guest speakers, Brian Peters, who spent years working with customers around the world, defining specific solutions for force and torque measurement. We also have our load cell design engineer, Jacob Wallstrom, who's joining us to get into the more particular details about performance, accuracy, and what makes a good load cell. So we're going to start this event. It is recorded. We'll be posting this on our YouTube channel as well as sending you a recording if there's any place that you'd like to reference or share with others. So let's go ahead and get things started. Our agenda is going to cover a lot. So we're going to move pretty quickly through load cell definition, how it works, and types of load cells. What we really want to get into more detail on are the specifications, anatomy of different load cells, the inner working, strain gauges, flexure, and model design, and what considerations are made by engineers when designing load cells. Then we'll talk about moment and temperature compensation, calibration, and cover some FAQs that go directly to our engineering team about load cell design. So with that, I'm going to turn it over to Brian and Jacob and let you get started.
All right, thanks, Jamie. Really excited to get to talk with you all today. Thanks for taking time. Like Jamie said, we'll be bouncing through a few of the sections pretty quick and allowing more time to deep dive on the technical. At least that's our goal today. So we got to start with the basic definition, make sure we're all starting from the same foundation. So load cells, I'm sure most of you are well familiar with them, but essentially it's a transducer, which is converting mechanical force into an electrical signal. So they can be configured to design, or they can be configured to measure a variety of forces, whether tension, compression, axial, torsional, shear, bending moment. And then, of course, we can combine design aspects to be able to measure some or all of the above. There's no moving parts inside there other than a metal element that is deflecting a very small amount. But there's really no wear and tear, and properly used, load cells get better with age and can last indefinitely. So general overview. So we're going to be talking a lot about design, different details, different design aspects. Why does it matter? Well, pretty obvious. It's going to directly impact the accuracy of a measurement, the general performance of the product, and the performance from your test, the quality, the durability, and of course, how well suited are they for different applications. So how does load cell work? Jacob, I'll hand it over to you.
All righty. Yeah, so load cells basically work by bonding strain gauges to a spring and wiring them in a way so that it's a Wheatstone bridge, so that it can convert the change in resistance of the strain gauge to millivolt per volt output. And that's going to be ratiometric to the force applied. So a Wheatstone bridge looks like that right there. It's basically a voltage divider. And the output is going to be that VO there. And on the next slide, the resistors are actually strain gauges. Those are the parts that are sensing the strains. And some are going to be designed to increase in resistance as a tension gauge. And some are going to be designed to be in spots where the resistance will go down as a compression gauge. And this is kind of an example of why the strains are causing that change in resistance. You can see the top one there, it's kind of in tension, and it kind of just stretches the grid or the strain gauge there to where the resistance goes up because there's less cross section for the electricity to go through, and vice versa there with a compression gauge. And it's very important when designing a load cell to have the tension and then the compression strain gauges matched in the strains that they're seeing, so that the change in resistance is matched. And that's important for a few reasons. But one of the main ones is that as soon as the left and the right side, the black and the red side there, aren't matched anymore, then the current going through those two sides of the bridge isn't the same, and that'll cause a different voltage drop over the strain gauges that isn't correlated to the change in force. So that'll cause some nonlinearity issues. And to give you an example of how sensitive load cells are, for most of our load cells that have 4 millivolts per volt output, they only need a change of 1.4 ohms in order to reach that full scale output.
All right. So real quick, we're going to cover just general types of load cells. They come in a lot of different form factors, package size. There's different either application or design parameters that are going to be driving these different shapes and sizes, but we'll go through just some of the more popular families here, just as general review. So pancake or low profile, Interface makes more of these style load cells than anyone else in the world. It's certainly what we're known for. S-type, a good versatile sensor, shear beam, rod end, load button, load pins, multi-axis, canister columns, and then some bending beam solutions. So next slide. So here's our low profile. As I mentioned, we make quite a few of these. Capacities ranging from everywhere from 25 pounds above 2 million pound force. Tension, compression only as dictated on the model on the right, or of course universal, which most of them are. Very versatile, very hardy, rugged sensors. They're good at accepting various application aspects, which you'll better understand when we get through the rest of the presentation today. Offered with an optional base, which we always recommend. And then, of course, we offer many, many different custom variations on this family. So next. S-types come in different shapes and sizes as well, somewhat driven by either dimensional constraints or desired capacity ranges or ceiling parameters. Good versatile also in terms of being able to fit most applications pretty well, relatively compact and relatively efficient from a package standpoint, and also efficient from an economical standpoint usually. So performance is good for most of these models, just not quite as rugged or insensitive as the LP is to various less than ideal application aspects. But we make and sell quite a few of these. And of course, most people think of this as when they think of a load cell, they think of an S-type. Interface founder actually invented the first one and probably should have patented that, what was it, 56 years ago. So, all right, next slide. So shear beam, also common. These are pretty compact, especially from a vertical standpoint when you integrate them into a setup. Relatively stiff, but good high strength and easy to seal. So they lend themselves well for various weighing applications, scale type applications, or if you just need something that is relatively compact and small for a relative load capacity. Bending beam and double bending, these are also very common, real popular for integration into machines, typically lower capacities. And we offer a couple different flavors of these, which we'll show from a flexor standpoint that bring different feature sets depending on the model family there. Canisters columns, these start to become good options as capacity increases. They scale in size against capacity better than, say, maybe an LP from a weight standpoint. They can perform very well if you have good instrumentation to support them. We actually use some of these in some of our calibration frames for reference. Linearity and such may not be quite as good as some other models, but if you can scale that in your instrumentation, it's a non-issue. But again, we can seal them pretty well. That second unit in from the left there, from the right, excuse me, the all blue one that has very high hermetic properties, fully welded construction, Class B connectors, for example. So we can develop these into different ultimate form factors depending on what's required for the application. Rod end, also very common, mostly because they're easy to integrate. When you've got mechanical threads on both ends, it is usually pretty easy to get in line into a load string, and they're also a relatively small diameter. So if you have multiple loads in a test setup and maybe have some radial constraints, these are a good fit. Good in just general push-pull testing. And then we also offer some products such as our WMC there, which actually get quite small and end up being fantastic options if space is a constraint. And we can also offer these with some pretty high hermetic properties, fully welded, for example. Load buttons. Load buttons often get a bit of a bad rap just because performance isn't quite where it is with other sensors. But when you factor in all of the design constraints and compromises there to get to very, very small form factors, it's not to be surprised. Interface, of course, has done some tweaks, which we'll highlight on a couple, on one product family to try to bring interface level performance to this type of product. But sometimes these are the only option or the best option. Some of them have mechanical attachments, and some of them require different ways to secure in the test setup. But definitely have their place in the force measuring world, and we've, like I've said, have tried to raise the bar when it comes to the convex BT as well as our LBMU. Load pins. Load pins are becoming increasingly popular. Very easy to integrate into existing test setups or machines, I should say. Replacing a bolt with a pin is an easy way to get a desired force, whether it be axial or even maybe biaxial, the dual axis setup. They lend themselves to be pretty easy to seal and ruggedize. And we even offer some that are submersible for use in subsea, harsh environments, and of course we have wireless configurations. So if integrated properly, you can get good results from these as long as you take some of the integration and dimensional aspects into consideration. So load pins, definitely a good option to consider. Multi-axis, also a growing market for us and for our customers. Essentially, you're looking to integrate more axial measurements into a single sensor. Sometimes you can do that through different load strings, different integration locations and test setup, but sometimes it makes more sense just to package it into one sensor. Additionally, they're great for verification on are you actually imparting the loads you think you are to your DOT. So you really get a much better picture of what's happening from a force standpoint. And again, these can come in 2-axis, 3-axis, axial torque, axial bending, axial shear, and we'll dive into some of the flexure differences, for example, from a design standpoint, to accommodate some of the different force measurement needs here. All right, specifications. Okay, so I think I'm still covering this, right, Jake? Before we dive into specifications, I think we just want to touch briefly on, the selection process. How do you identify what's the right load cell? It's going to come down to a few things, driven primarily by the application details, right? So it starts with what type of measurement are you looking for, what type of force value are you looking to get, mounting considerations, dimensional constraints, obviously the capacity, as well as potential side loads. But then, do you need different material and or environmental considerations? All right, so mechanical, electrical, environmental, and performance. I think these do a pretty good job of summarizing things that need to be considered. So starting with the mechanical front. Next slide. Starts with usually capacity. What is your desired test range? Are you going to potentially need to have some overage there in terms of ability or inability to control the load? And then also, how do you handle your load range requirements versus maximizing resolution, right? And making sure that your measured range gives you as much signal to work with as possible. So most sensors are going to be rated capacity with 150% safe overload. And most sensors, again, will have mechanical damage and around, anything above 150%, will usually start to cause a zero shift with most sensors. And then, of course, as you approach 300% or maybe 400% for some, you'll start to look at actual mechanical failure. So that's something to take note of on specification sheets, of course, and make sure that you're properly selecting the load cell from a capacity standpoint. Also, as I mentioned earlier, you take into account if you're going to have any extraneous loads. Are you going to have any torque, side load, off-axis loading? Many sensors are better at handling this than others. So it's something to take a look at. We'll go through some mechanical details in terms of how you try to reduce this. But even through strong efforts, oftentimes we see a lot of customers that are pretty sure they don't have any side loads that once they get a multi-axis sensor confirm they are actually getting some transferring through into their test article. But general rule of thumb, if you've got a tall, skinny sensor, obviously it's going to be more sensitive to bending, for example, or side loading versus a lower, wider sensor. But again, it's going to come down to the flexure design, which I think we'll be able to share in more detail here later. So next slide. Mounting, how you attach to that sensor is so critical. The accuracy of the measurement you're getting is going to come down to how well are you imparting that test load directly through the sensor. Obviously, you don't want to have any parasitic loads, but depending on how you need to integrate that sensor could drive different sensor solutions. Again, if you don't have any way to attach to it, you may be looking at gluing in a load button, for example. But most sensors are going to have pretty easy inline connections on both ends. But again, if it's compression only test setup, for example, you'd be looking at possibly just using a compression load button style solution on one end of the sensor. So keep that in mind. Next slide. When you are integrating, it's important to keep track of live end and dead end. We'll show how this correlates through from a flexure level. But the easy way to track this is where's the connector or the cable located. We're going to have the gauges in the strain gauge area, the bridge area, in between that and the live end. So on the LP on the left, the top hub is the live end. The dead end, then the reaction loads all transfer through the outer ring down into the bottom of the base. And on the S cell on the right, again, the gauges are going to be behind that cover there, which we'll show. And so again, you want to make sure that you can't have any potential inertial influence from the cable if it's a dynamic test, or a parasitic load if you've got that cable strapped down and trying to load through on the dead end, essentially. Next slide. So how you attach to it is important. Generally, you want to make sure that you have good, high strength, tight connections. You don't want to have a lot of slop in the system. That will have an immediate impact on linear hysteresis in your test setup. It's good to pay attention to some of the options from a compression standpoint. You typically want to utilize a spherical or curved surface to ensure that you aren't putting any unwanted bending loads through your test string. So in fact, all of our compression only load cells will have a spherical loading surface on the top. So you'd want to have a flat surface interacting with that as depicted on the picture on the left. Our cal grade sensors come with pre-installed cal adapters, which oftentimes customers don't notice, but the tops are actually spherical. So you have the choice of loading through the threads or directly on the end of that if it's compression only if you want to. But basic test setup is well depicted on the right with essentially some rod end bearings to decouple the sensor from any potential side or bending loads. May not be able to do that, but that would be the preferred setup, of course. And that way you ensure that the only loads going through the sensor and through the bridge are going to be axial in nature. On the electrical side, most force sensors, torque sensors, again, given that they're going to be Wheatstone bridge based, will be a millivolt per volt output. We can offer amplified options. When would you need that? Well, you have high cable runs where you may not be able to support sense, which we'll talk about here in a little bit. Or if you have a noisy electrical environment, high level signals obviously will typically work better there. From an accuracy standpoint, of course, carrying that millivolt per volt signal into your instrumentation is preferred. You're not adding an additional layer there of amplification or even A to D resolution concerns if you convert to, say, a digital signal. But paying attention to grounding is important. We can help you out in terms of recommended grounding protocol depending on the sensor. We want to avoid grounding loops if you can, for example. So electrical signal, pay attention to that. What do you need? And then thermal. You're going to have some unique environmental. Most millivolt per volt sensors, we can provide solutions up to 500 degree F. If you need high level, usually the electronics will start to be limited around 225 degree. So keep that in mind. But thermal also has an influence on zero span, which we'll get into in a little bit. And so you need to pay attention to that, not only from the sensor itself, but also your mechanical setup. So sometimes it's good to do qualification testing or characterization, I should say, from a thermal standpoint, if you can, to remove some of the error and some of the uncertainty. But it's often best to do it as a full assembly if you can, because every mechanical joint is going to respond, of course, to temperature change differently. Next slide. And then moisture, humidity should be pretty straightforward. Different sensors have different levels of sealing, as we'll show. If you have moisture or high humidity, make sure you're properly selecting the right sensor, and also pay attention to your cable. We often have situations where moisture can weep up through the cable, and despite best efforts to seal the sensor itself, it makes its way in. So really make sure you engage with the application engineers or look at total system aspects. Next. All right, now we're going to start to get into some of the specifications. So some of you may already know these. This is something we like to touch on a lot, but I think this is good core understanding here for accurate force measurements. Oftentimes customers ask us, what's the most accurate sensor you have? There isn't really a spec for that. It's going to come down to a lot of different parameters in terms of specific load cell performance aspects, but then also application details in terms of how you're using it, integrating it, what else you're hooking it up to, right? But under the accuracy folder, if you will, or bucket, there's a few things here in particular that we can speak to, and we can certainly more importantly test to, which is what we do with every sensor that we calibrate and ship. Static error band is going to be a combined value, which we'll show here, but we've got nonlinearity, we've got hysteresis, non-repeatability, creep, side load, centric load. So we're going to touch on most of these today, and then also touch on temperature later. But it's important to note how the different specifications impact from a unit standpoint, right? Whether they're a function of your reading, whether they're a function of change as in temperature, whether they're a function of full scale value. So even though you may be using a portion of it, now that error starts to take up a larger portion of your error budget, if you will. So let's dig in a little deeper here. So specifically, nonlinearity hysteresis, pretty straightforward for force sensors, as with most sensors. We want to ideally have a perfectly straight line output as a function of signal versus applied force or torque. However, the reality is there's going to be slight deviation against that. So the deviation from that straight line is going to be the nonlinearity. So if you're ascending from 0 to full scale, what's that max deviation from straight line? That's going to be the nonlinearity spec. And then what we test for also is hysteresis, which is what happens when you release the load and you start to now descend in force. And so we'll test for that and to make sure that we capture what the hysteresis value is. Hysteresis is a mechanical function that traces down to the material, and it exists in everything in the real world. So it's something we want to make sure we test for and can provide data on. Both of these are usually a function of percent full scale. Now, if you want to try to summarize a sensor's performance, SCB is typically the best way to look at it, and that's a static error band. So it's looking at what is the deviation from a best fit straight line, both for the nonlinearity and also for the hysteresis, as well as capturing the non-return to 0. So you have that error band there, and now you have a new output line that bisects that, and now you have a percent deviation as a function of the breadth of that band, and then you also have a new output value in millivolt per volt that can be used that would do the best job possible to incorporate any potential nonlinearity or hysteresis change in signal across through the whole operating range. So that's SEB and SEB output. We have that listed specifically on many of our data sheets. It's something good to look for. So non-repeatability is listed. This is something that sometimes customers get a little confused on, but it's the maximum difference in output under identical loading conditions and environmental. So if you take the sensor out, put it back in, that's obviously not going to be a test of non-repeatability. But this is a good value you want to have from a calibration grade sensor standpoint. If you have consistency in how the sensor performs, then who cares about the nonlinearity? You can usually take that into account in your instrumentation and or software. And as long as the sensor has good repeatability, that's going to lend itself to be a very, very good calibration reference standard, for example. So just pay attention. There's a lot of things that roll into affecting that, but we do specify it as a % RO. All right, and then the mechanical aspects, eccentric load, side load. So these are actual specs that we list on all of our moment compensated load cells. So all of our low profiles, which will be our 1000 series fatigue, our 1200 series workhorse, precision model, as well as our 1100 series premium precision family, we will spec out the eccentric and side load sensitivity on there because we test for it. It's something to pay attention to. Sometimes you can't isolate loads. You need something that's going to be rugged and deal with it. Well, I recommend you go with interface low profile, because we'll be able to tell you exactly how it performs, which we'll show in a little more detail here. All right, Jacob, let you handle creep.
Alrighty. Yeah. So creep is basically the time delay of output. So it's the change in load cell signal over time with identical loading conditions. So kind of the way I think about it is if you took like a conventional spring and put a weight on it, it would kind of change a certain amount of distance. And even after that, it'll still creep a little bit more. And that's kind of a property of materials, of springs. And load cells are able to compensate for this phenomena. Next slide, please. So that graph on the right, I think, does a pretty good job. So every spring or flexure or element, depending what you're calling it, the metal that you're bonding your strain gauge to is going to have a positive creep characteristic. And basically, the strain gauges can be designed in a way as to kind of counteract that. So the flexure will still deflect more over time and creep, but the strain gauge that gives the output is able to creep a lot less. And this is a pretty important aspect you should be considering. If you were going to measure force and correlate it to deflection, deflection alone, the deflection will creep 10 times the amount that millivolt per volt, strain gauge output would give. So our 1100, 1200, and 1000 series have a creep of 0.025%, while 1800s get down to 0.01%, and that's in the first 20 minutes. And creep does decay exponentially. So the first couple seconds, you're going to see the most drift, and then 20 minutes, you'll see a little bit more, and then the next 24 hours is equivalent to the amount of creep that you see in the first 20 minutes. So unless you only wait more than 20 minutes to get a reading, you definitely want to creep compensated load cell.
Yeah, real quick on that, two things. Pay attention to how creep is specified, because it's against time. Oftentimes, you may see a spec there and not realize it's over a longer or shorter duration. So make sure you're comparing apples to apples on that. Secondly, if there is any concern around, well, how much creep am I getting in my test? Creep will decay out of a setup as it's introduced symmetrically. So if you were to finish up a long duration test and you immediately remove that load, you will see a non-zero value in your instrumentation, and then that will decay back to zero condition in a symmetric manner to how creep was introduced. So you're going to see a lot of that come out quick and then start to exponentially return back here back to the final zero value at a very slow rate there. So easy way to check just how much creep are we getting into a test setup.
Sweet. And I think this is going back to you, Brian.
All right, so I'm going to cover just kind of high level the major components of a load cell. Jake's going to do a deep dive on gauges and flexure elements, but primary components for most sensors are going to involve three aspects. What we refer to as a flexure. So that's the primary machined element that acts as the spring. That's what's seeing the load. That's what deflects. Very specific parameters there, which we'll do a deep dive on. Strain gauges. Strain gauges are the heart of the sensor. The quality of the gauge, quality of the temp compensation, the quality of the bridge completion, all that play a huge role in terms of the quality of the measurement that you get out of that sensor. So we're going to do a deep dive on those, and the electrical connection. So how are you taking the excitation to the bridge, and how are you getting the output signal out of the sensor, right? So it might be a connector, it might be a cable. Anyway, so here's a couple different types. Here's an S cell. So this is an SSM model in particular. So the gauges are going to be inside that round pocket. We'll have a cover over that. It'll be sealed up. The live end, as depicted earlier, on the top. And I think you can start to see how, if you have it bolted on the bottom, that live end is going to be the closest to the bridge, right? And you won't have the cable then influencing anything either, because it is past the area where the strain gauges are, where the bridge is. So live end, dead end, always good to note when you're installing a sensor. Next slide. Here are 3 different mini beams. You can see the flexure designs here. The 2 on the left, cables would be bonded to the side of the flexure with a cover over them. We have 2 different flavors there. The one all the way on the left is a standard MB, so it's a standard mini beam. Gauges are on the top of that very thin area. Dead end on the left, and then the live end on the right. Again, you can start to see how dead and live make sense depending on where the gauges are. Again, that cable would be exiting on the left. The middle model there has an example of mechanical overload protection. So this is how we incorporate that on different models. I think we've got a few more examples later on too. But the middle MVP model has a very small gap there that when the flexure reaches a certain amount of deflection, or i.e. force, it actually transfers the load away from the thin section where the gauges are and transfers it to the middle central column, which will allow for things like 10 times safe overload protection. So you can take a 10-pound load cell that's very accurate across 10-pound range and apply up to 100-pound force without damaging the bridge. So same on the right, similar approach there with the MBI model. This one, you can see that there's a little groove there for the cable exit on the top. The gauges are typically across the top on this model, again, where the thin beam sections are. One unique thing about the MBI is these are actually moment compensated as well. So we'll actually go and adjust and make sure that it's less sensitive to where you apply the load on the live end, which is the 2 holes on the right, to where you can kind of do a point load anywhere around that area, and it's still going to measure that vertical force quite accurately. So just a good example here of how we can take similar form factors and offer different solutions around that. Next. Load button. So pretty straightforward design. You're going to have varying levels of thickness there on the top. Gauges are applied underneath that. You've got the load button there directly on the top in the middle, and it reacts through the outer ring. These are typically sealed underneath with a diaphragm. You can barely make out the lip there where we would seal that. And then depending on the model, it may be welded, maybe glued. It just depends on the particular model. Cable exiting through the middle of the body there. Next. And here's our little profile. Quite a bit more going on here. We'll start with the live end there at the top, what we often refer to as the hub. So the load cell then reacts through the radial shear beams, which you can see look like kind of some spokes out to the outer ring, which gets bolted to the base. The base has a symmetric female threaded hole in the bottom, like you see in the live end there, which allows itself to integrate into test setups quite easily. If you were to just buy the load cell by itself without the base, you can certainly bolt it down to a plate or whatever the rest of your test setup is. Just obviously, we recommend the bases. It just makes it easier and don't have to worry about hardness and flatness of that surface for best performance. So, but other details, starting at the top, I guess, there's the diaphragm lip where we would actually secure the diaphragm and seal off what we consider the gauge cavity. There'd be a diaphragm on the top and the bottom of the gauge cavity, so above where the base is. We have the strain gauges in there, you can see, some of the bridge completion wires as well. Obviously, the connector coming out of the side there, that may be an integral cable, it may be 1, it may be 2, 3 connectors, depending on the bridge count. And then there's the mounting ring. So our LPs in particular have an inner and outer mounting ring to, again, ensure that we precisely control how that force loads through the outer ring, which, because it makes a critical difference in what those beams see from a strain standpoint. And I think Jacob's got some good FEAs to show that later on. So next slide. So you've got the basic load cell, and as I said, you can have many different flavors from there in terms of customization of how many bridges, what kind of connector do you want, cable, do you want wireless, base, no base, what type of threads do you want? So a lot of features can be customized from those core elements of a load cell. Next. And accessories. So everything that goes potentially in or around the load cell, whether it's rod ends, thread adapters, shunt cowl resistors, clevises, mounting plates, bases, or even simulators. So a wide range of accessories to go along with that. You want to talk about Sense for a little bit?
Yeah, yeah. So Sense is going to kind of give you an idea of kind of a engineering approach to the complete load cell to data acquisition system. So if you think about Wheatstone Bridge, the output is directly proportional to the applied voltage or the excitation voltage. And so if you had a long cable run or a cable run going through a place where there's going to be temperature fluctuations, there's going to be a voltage drop from your supplied voltage all the way over to the cell. And what can happen there is that you apply a certain voltage, and when you normalize the output by that voltage, you're actually normalizing by a value that isn't actually getting to the bridge. And that can happen from a simple voltage drop across a cable. It also can happen if the cable is going through, let's say, an oven where you're changing temperature. The resistance of that cable is changing as well. So the voltage being applied to the bridge is going to fluctuate as well. Uh, Interesting note is that really only the excitations need sense. And that's because the excitations are carrying current to the bridge, while sense or even the output has almost no current flowing through it, so there's no voltage drop. It's measuring pure voltage. So that's a really important feature.
Yeah, I just want to add real quick. All of our cables will support 6-wire. So even if the sensor is not a 6-wire or sense-enabled sensor, the cable will allow your instrumentation to actually read what that voltage drop is. And again, this all goes back to the fact that load cells are ratiometric, right? So that cal data is a function of 10-volt excitation or whatever the voltage is on that cal cert. And oftentimes customers don't realize that it's not quite getting what they think is getting to the sensor. So 6-wire, if your instrumentation supports it, always a good choice, whether it's just in the cable or as we do on many of our calibration grade sensors, we'll actually take the sense all the way to the bridge level. So through the connector and to the solder pads for the bridge. So ensuring maximum accuracy there.
Mhm.
All right, Jacob, back to you.
Thanks. So now we're going to talk about strain gauges a little bit. So there's different styles of strain gauges, but they're all doing the same thing, right? They're all measuring strain along a certain direction. So you see there's linear, shear, Poisson, and chevron gauges. And ultimately, so long as the grid lines are matched up to your strains, you're going to be in good shape. And we'll talk about grid lines here in the next slide. So here's a strain gauge up close. And the grid lines are those thin lines that are going across the gauge. End loops are the thicker sections at the end of the grid lines. The solder pads are what you make your connections with. The fiducials, those can look different for different types of gauges, but they help you align your strain gauge, which is very, very important. The backing, that's what your foil is bonded to, and that's also what you're going to use to bond to your spring or your flexure. And number 6 is going to be an optional encapsulation. That basically just protects your grid lines. And yeah, next slide.
Jacob, when would we do the encapsulation? When would that be a good choice?
Yeah, so it kind of depends. Most of our gauges, we don't use the encapsulation. We'll put a conformal coating over top of it. There's some applications where maybe it's like where outgassing is a concern, where some of the conformal coatings you would want to put have some outgassing issues. So the encapsulation's an easy way to kind of avoid that issue. Alrighty, and so gauges can be compensated for a variety of different issues. Self-temperature compensation. This is when the strain gauge can be compensated to kind of match its thermal expansion to the spring. So you can think about if you use the same strain gauge on an aluminum spring and a steel spring, those springs are going to expand and contract differently with temperature, and you want to match your strain gauge to it, and that avoids some apparent strain that isn't correlated to a force. And then on the right there, modulus compensation. If you remember back to mechanics of materials, the strength of a different material, the modulus of elasticity, that can change a little bit due to temperature. So if you're measuring force, in the outside in the winter and it's 40 degrees, and you're on that same test in the summer when it's, here in Phoenix gets pretty warm, the material properties of your spring change, and that can affect your output because you have a weaker spring. The gauge can be compensated for that. It can basically change its gauge factor so that it offsets any loss or gain of strength of the material. Next slide, please. So there's two main types of foil gauges. There's plenty more, but these are the two main ones. We'll start with Constantin. It's a copper nickel alloy, and that makes it very easy to solder to. It's a little bit less thermally sensitive. It warms up quicker. It's a very common material, but there are some drawbacks. It has a lower gauge factor, and it's not as easy to heat treat, especially to the extent that you would need to, in order to have self-modulus compensation. So if you want to modulus compensate a constant bridge, you have to add modulus trim. So basically special resistance on your excitations that change their resistance to basically lower the voltage applied to the bridge. And constant gauges are best suited for room temperature applications. They're definitely not good for high temperature applications. And we switch over to Karma. That's what Interface uses. It's a nickel chromium alloy, and it's able to be heat treated in a way that makes it way more conducive to self-modulus compensation. So it doesn't need extra trim in order to modulus compensate, because that'll reduce your output. And in addition to that, it also has a higher gauge factor, which means better resolution, better performing load cell. It's a harder foil, so it makes it a little bit harder to roll, but it does lead to a little bit better performance, and definitely is more reliable at high temperatures. It's not as common of a material, so it's a little bit harder to source for some companies. But Interface has been using this, I think, since the beginning, right? 56 years. So it's pretty much our standard. So all these drawbacks really don't bother us all that much. And in the top right, you'll see the gauge factor formula. So this is, a property of the foil, and it's basically what correlates the change in resistance for a given strain. So a higher gauge factor for the same strain means you're getting more output for the same amount of deflection or strains. And that's really important for fatigue life, which is why we use Karma. Next slide, please. So how is a gauge made? It's very similar to the process that's used to make what we're all using right now, right? Computers. It's photolithography. So the foil is going to be bonded to the backing, and then there's going to be a photoresist applied over top, and using a mask and a UV light source, the photoresist can be hardened in certain locations that then reveal the foil that we're going to etch away. And once all that's done, you're left with your gauge. Next slide, please.
Jacob, that's the process Interface uses to manufacture our proprietary gauges, correct?
Yes. Yes.
All right.
And all right. So switching over to putting the gauge on the flexure or the spring, you're going to want to make sure that your grid lines are aligned with your strains that you're trying to measure, that you're trying to correlate to the force. So grid lines not aligned with the strain will be less sensitive to that loading mode. So that can cause nonlinearity, and other performance issues, but it also is how multi-axis load cells work, where some gauges or the bridge that's wired with those gauges are more sensitive to certain loading modes than others, and that's how you get a multi-axis cell. And then I think we have an animation coming up here. Could you click to the next? There we go. So you can see the grid lines there are aligned with the principal strains, and that's from a simulation. Might be kind of hard to see on your computer screen, but those are little arrows kind of pointing in the way that the material is deforming. And you want your strain gauge to be in a uniform strain field. And that's really important because that can cause nonlinearity issues. And it's also something you want to take into account because assembly is never going to be perfect every time, right? So you want to make sure that a gauge that's a little bit high, a little bit low, a little bit to left or right isn't going to throw off the performance of your load cell. Next slide, please. So kind of going back to the tension and compression that we talked about earlier, you can see in the photo on the bottom left that the grid lines on the right are directly aligned with the strains, while the grid lines on the left are 90 degrees to that. And so the one on the left is going to be the compression gauge. And you can kind of think about how it's going to stretch the grid lines kind of hamburger style, right? While the one on the right is going to stretch it long ways, which is going to increase its resistance. Right. Next slide, please.
Actually, Jacob, if I can touch on 2 points here, this is
totally.
This is a great view. So, 2 things. First, as he's highlighted, depending on where the gauges are and how they're placed, they're going to respond differently to the load. You only need 4 gauges, as we saw for a Wheatstone bridge, but interface on our low profile load cells will utilize 8 strain gauges per bridge. So we'll actually place the gauges in a manner that if there is by any chance a side load introduced, a bending moment, the various legs will self-cancel. So it will not manifest as a change in axial force measurement. So not only is the low profile design radially symmetric, which lends itself well for handling any non-axial load, we use 8 strain gauges, and then we do another step further called moment compensation, which we'll touch on. But I just want to highlight that. So through the design of the flexure, through the placement of the gauges and the types of gauges used, we can make these sensors very robust to reject anything other than measuring the actual axial force that's popping up. The second thing I want to highlight here is if you go through some of our products, you're going to see that, as you saw earlier, our standard 1200 series has the female threaded hole in the top, right? Well, if you look at this, you can see how the force applied at the end of that top section, which would be threaded, transfers all the way through the center portion out to the outer beams where the gauges are. So our 1200, our 1100, or 1000 series will have a female threaded hole. We talked about the importance of mechanical mounting and the thread engagement and making sure you've got good tight connections and potentially even preloading. That is because it lends itself for much better consistency of how that load propagates through to the bridge. So if you look at our calibration grade sensors, for example, our 1600s, they have a pre-installed cal adapter. So that center stud that we see here in this picture would be threaded in, it would be locked at the factory, and it would be preloaded to ensure that as you operate within the capacity, you're not going to get any change in how those threads interact with the center hub to ensure that you don't get sudden shifting of which threads are loaded, where the load goes through, which can then dictate a very slight, subtle change to the beams, right? Now, our 1800 series takes it one step further and is what is depicted here, and it's a feature we call an integrated stud, where it's all part of the same machined element. And we do this for some of our more demanding applications, some customers that really want the best performance. We'll do an integral stud. So it's all one machined element, and it completely eliminates the chance of any variability there in terms of how that force is introduced much further away from the gauges and then propagates down through consistently every time to where the bridge is. So
that's a good point too to bring up the 1800 series, because not only do they get the integral stud, they also get double gauges, and you can see that the nonlinearity of one gauge being misaligned one way or the other is somewhat random, right? So by doubling the amount of gauges, it can help cancel out any nonlinearity issues.
That's 16 gauges, right, per bridge?
Yeah,
So
16
quite a bit.
bridge on 1800s. Yeah, yeah. Alrighty, thank you, Brian. Next slide, please. There we go. And so we talked about creep and creep compensation before, and how that's achieved is by changing the end loops. So the end loops, the longer the end loop, the more positive creep response of the gauge. And you can kind of think of that as the longer end loops, the bigger end loops kind of give more anchoring to the gauge. So they're kind of like responding more like the flexure is. And we can use the end loops to basically match. That's how we match the gauges to the load cell and that capacity. And then the backing is also pretty important when it comes to creep compensation as well. That's what's transferring all the strains from your flexure into your foil, which is changing its resistance and leading to your output. One other interesting aspect too is the distance from the foil edges or the end loops to the edge where the gauge is cut is pretty important. If it's too short, it can basically kind of act like a different end loop. So next slide, please. Why do we make our own strain gauges? I actually think this answers a question in the chat of are the modulus compensation done at in the load cell by interface or in the cable and signal conditioning? So that's a good question. Interface, we heat treat we make our own gauges, we heat treat our own foil, and we're able to thermally match the performance of the strain gauge to our materials. So we do that in-house. We qualify every lot of gauges for these characteristics, and that's pretty unique. So we match our gauges to our flexure material, and since our gauges are karma and we're able to modulus compensate them due to that heat treating process, they don't need the compensation resistors that even further reduce your output. So we have higher output, better resolution than a lot of other load cell companies. And one point we're going to touch on a little bit later too is this gives us opportunities to optimize the gauge and the flexure as one cohesive design, which we'll talk about in a little bit. Next slide, please. Thank you. So now moving on to the flexure or the spring design. So we'll start here with the low profile. That's kind of the bread and butter of interface, right? It's a web shear design. Let me pull up my notes real quick. So you can see there's a lot going on with a low profile, an LP. It's an assembly design, so typically, right, it's got the flexure as well as the base, and there's a lot that goes into it. So we want to balance quite a few parameters to make sure that we got the best performing load cell. So you see there the beam height and the beam thickness. That's basically going to control the stress at your gauges or the strain at your gauges. And that's very important because not only does it control the relationship between force and strain, it also determines how the strain is kind of flowing through the flexure. So remember before how we talked about the strains need to be aligned with the grid lines. If your beam is maybe a little bit too short or a little bit too thick, you can see how you'd start to get more bending than true shear. And so the strains wouldn't be aligned with your grid lines anymore, and you start having performance issues. We want to concentrate the stresses at the gauge. That's really important for performance. It also is just good design, and you're going to avoid a lot of stress concentrations that way. Except you can see on the beam height there, we have that little notch that kind of is acting as a stress concentration to make sure that the gauge is seeing the most stress. That also helps in what Brian's going to talk about a little bit later, which is the moment compensation. That gives us kind of a nice radius to mechanically moment our load cells. A few of the assembly aspects that are important when it comes to an LP, since this is going to be bolted to something, right? Hopefully a base, but if you're doing it on your end, it's going to be bolted to hopefully a hard flat surface. And the flat surface is pretty important. So you see the loading rings on the right. Those are used to keep the contact surfaces flat and also perpendicular to the applied force. And that's really important because you can kind of imagine if the load cell wasn't sitting quite flat and you were applying a load perpendicular to a flat surface, you would not be applying that in the, you'd have off-axis loading is what would happen. Another thing too, the bolts, we typically have, about 1 bolt per beam, and that's important, right? Because the bolts are basically acting as what's keeping the dead end truly dead. And so the bolts have to really torque down and hold the assembly so that the live end is the only part that's moving.
Hey, real quick, I want to highlight something too.
Yeah.
If anybody's spent any time on our data sheets or has used a lot of our low profiles, you'll know we offer different capacities all within the same form factor, right? So we'll have a 1210, a 1220, a 1232, or vice versa for the other series. And what we're doing there is we're varying the beam dimensions within the same package, or maybe even varying the beam counts. Maybe we cut some of the beams out. So it allows us to have a little more manufacturing flexibility, but then also be able to standardize more on the customer end in terms of integrating with different sensor types or different capacities, excuse me. So obviously we reach a certain point where we have to grow that the diameter, and then we fit another range of capacities within that, and that's all through changing the internal dimensions there of the beams. So
good point. Thank you, Brian. Alrighty, so now we're going on to the LBMU. And this is a load button. And load buttons, as Brian kind of mentioned before, get a bad rap. They have their pros and their cons. Load buttons, they don't transfer moments to the beam, right? There's no, fixed point of load application, which doesn't transfer moments, but it also can cause some linearity issues if you're applying the force in a different location than what was intended. And that makes these load cells very, very, very sensitive to gauge placement. So you can kind of see some rough dimensions here. This is a really small load cell, right? It's, I think, smaller than a quarter, maybe smaller than a penny. It's pretty small. And you can think about trying to install 4 separate gauges in very specific spots repeatedly. And that's going to be really hard to manufacture. It's going to be really hard to have good, consistent performance. So since Interface makes our own strain gauges, we were able to make an all-in-one. This is also called a patch gauge, and this means that the tension and compression gauges relative to each other are in the same location every single time, and the technician only has to install 1 patch. So this helps these load cells perform as best they can, and also be a cost-effective cell to manufacture. Alrighty, so next slide here. Now we got the MRTP. So this is Interface proprietary. We got a patent on it by LeVar and Mr. Burrow there. And next slide, please. This one is measuring torsion, torque, and it is overload protected. So you can see there that kind of blue highlighted surface. That is attached to a column that's going down the middle, and it has those arms that kind of go out with those EDM slots, and those EDM slots are overload gaps. So the load cell is allowed to deform a certain amount, and then it contacts those surfaces and can't deform anymore, and it's overload protected. So this is really important for low capacity load cells because they're very easy to overload, right? Even handling it or installing it, torquing down some bolts for to apply the load, you could very easily overload it. So this is a really, really good design, and you can see the raised surfaces there too. That's what helps keep the live end, the load application of that outer ring, from touching the dead end overload stop column. And another beneficial aspect of this is the beams are on the outside, so they're very easy to access for gauging and wiring. Alrighty, Brian.
All right. All right. So multi-axis and flexure consideration. So here's two different options to accomplish the same thing in terms of offering a sensor that will do FZ and XY shear. The one on the left, you can imagine, was one big spiral there. So those are essentially 3 bending beam sensors bolted together. You can actually see the little gauge potting there that covers where the gauges are with the white areas. So you can imagine that they all kind of tie together. So it works. There might be some compromises in terms of deflection, stiffness, as well as maybe introducing a little bit higher crosstalk, right? Because every single element there is going to respond to that force. So that's one way to do an FZXY shear, is to have them all connected. The one on the right there has a center section that's bolted in to discretely measure the vertical, and then it interacts with 2 different sections beneath it to then be able to transfer the X and Y. So it's just a different approach there, whether they're all in one or isolated as much as possible from a multi-axis standpoint. Next slide. So here's an example of our 6-axis sensors. These are obviously full axial as well as bending moment solutions. These are a little bit unique in that instead of having a discrete output where each channel gives you specifically an FX value or an MY value, there are 6 or in some cases 12 millivolt per volt channels coming out. And the reason for that is internally there's various beams that's pretty representative there in this drawing here of what it looks like. Often called a Stewart platform or a hexapod, but each one of those beams will have strain gauges on it, will have a bridge on it. But it's not necessarily designed that each one of those beams is going to measure and provide the output for those different axes you're looking for, right? So instead you get a composite output with everything, and through calibration and characterization of the sensor, and then typically through calibration matrix adjustment on the instrumentation side, which is why we always recommend one of our BX8 amplifiers with these units, so you don't have to do the math yourself. You can then isolate and calculate out what the discrete outputs are for each channel or each axis, that you're trying to measure. So here's an example of, again, a multi-axis where instead of having a bridge that is specific to the axis of measurement, you have many different millivolt per volt signals coming out, but through very careful and accurate calibration, you can characterize how a specific applied load impacts each one of those millivolt per volt signals, and then be able to run that into your instrumentation. All right, next. So load pins. Load pins are typically hollow pins, so center of the flexure will be drilled out. The flexure design is going to be a function of the application dimensions typically. Most load pins sold are custom, right, in terms of either the diameter or the length or where the loading surfaces are for that setup. But the key takeaway there is they come in 2 flavors. They're going to come in either an internally gauged solution or an externally gauged load pin. And the externally gauged are going to have much bigger exposed pockets. They usually have to be potted, or in some cases like welds. But Interface primarily offers internally bonded solutions for load pin, much more rugged. We can seal off the ends of the load pin and protect the gauge cavity. So, but the important thing to note here is that the flexures are very sensitive to how they're loaded. So on the left there is a good depiction of what we would recommend for good performance. We don't want to bend a load pin. We want to keep it in double shear. So that means that the reaction surfaces, as depicted by those outer 2 elements, want to be tightly controlling not only the diameter aspect, but also the interface to the middle loading section. So as you push or pull that middle section up or down, you want to make sure that the stress concentration areas depicted by the grooves, again, if you reflect back to some of those other flexures where we neck down the material so that we can maximize strain. Same thing going on here. The gauges are going to be directly under those grooves, but that's where you want to have that double shear interface occurring from a system level standpoint. So it's really important you have tight tolerance, that you keep the pins in shear, and that you don't bend the load pins. So, all right, next.
Alrighty.
Sealing. Back to you, Jake.
Alrighty. So sealing considerations, right? This is directly related to the application and the environment the load cell is going to be used in. You can see there in the middle, we have a welded, kind of hermetically sealed 3200. And so we got the welded diaphragm. That's going to be top and bottom, as well as a welded, we call them a doghouse, where we put a lot of the tabs and perhaps an amplifier. And then we have a cable gland coming out here with the cable. You see here on the left, SSM. That stands for like a sealed S-style load cell. And it basically has a cable gland on one side, and then that internal cavity where we have the strain gauges, we kind of backfill that with a gel potting compound, and that helps seal the bridge from any moisture ingression. Then, on the other side, the right side there, the MB, that's pretty much exposed. So it still has a gauge overcoat, a conformal coating that we put on almost all of our load cells. But besides that, the wires and stuff like that are only protected by the that cover. So if you put, a screwdriver or something in there, you could ruin the load cell. And it really depends on the application, right? So we have some load cells that are being used, in oil drilling applications with 20,000 psi of oil around it. And then on the other side, we have load cells that are being used in high vacuum environments where everything needs to be vented and outgassing is a concern. So really working with the applications engineer on your unique environment and use case is really important in getting a load cell that's going to be good for you. Next slide, please. All right, and so we'll talk about flexure material types real quick. Obviously, the one of the main things to consider here is the strength of the material and the capacity that you're trying to measure. So you're going to see we use 2024 aluminum. It's low strength, but it's good performing, very low hysteresis material. However, it is limited to around 300 degrees because that's when the aluminum starts to temper again. Then if we look over at 4340 steel, this is super common, very easy to machine, low hysteresis, and it's very, very strong. So we use that for most of our LP range. Then if you're looking for corrosion resistance, it doesn't really get better than 17.4. It's very corrosion resistant. It has very high strength, but it has worse hysteresis than a 4340. So there's always going to be the drawbacks and weighing the pros and cons. And there's all sorts of other materials you could use, right? Titanium is one that's used for highly corrosive environments and maybe very hot situations where you still want an accurate reading. The obvious drawbacks there is that it's very expensive, very difficult to machine, and so it's very, very rare. And Brian?
All right. So we talked a lot about, design considerations, in terms of properly designing the sensor, making sure you're selecting the right components, the right materials, you execute the design. We're going to touch on a few extra things we do during the manufacturing process to try to optimize performance even better. So one thing that's unique to Interface is moment compensation. If you come across any data sheets for any of our load cells that has a side load or eccentric load sensitivity spec, that means it's a moment compensated load cell. So all of our LPs are going to be moment compensated. Our MBI that we referenced earlier, mini beam, as well as our SPI, which is a single point load cell, also goes through moment compensation. The minis are a little bit different process, but fundamentally still achieve the same thing. And that is that we will go in and actually adjust the load cell as necessary to ensure that it meets a certain spec when subjected to a pretty terrible off-axis load. So as depicted here, there's an LP bolted down to a base. If it's an 1100 or a 1600, that's going to be a base it ships with, for example. Otherwise, it would be a representative base, gets bolted down. This is before we put the diaphragm covers in, so the gauge cavity is exposed. Every unit, of course, is serialized, so the operator will load up that unit. It'll say, this is an 1100 series, this is the moment spec that we need to hit. And the operator then applies a pretty substantial load to it, much worse than would typically be seen in a proper application, at least. And we'll actually move that weight around 360 degrees and see how the zero responds to that. and then through mechanical adjustments of the beam, will ensure it pulls it within spec for that unit. So the goal here is that you can imagine almost an inverted cone coming out of that load cell, that as long as your load is applied within that, you're going to get very accurate axial measurements. So this is a very labor-intensive step that Interface does for every load profile, but this is how we can guarantee it meets our side load sensitivity and eccentric load sensitivity specs, which means you can throw it into an application and it's just going to work. And that's why people that have used it keep coming back for more of these. So next slide. This is a good pre and post snapshot of a typical load cell. Next slide, please. There we go. So here's a 1220 50K. The blue plot is the pre-moment. So every unit gets checked before. It's a good way we can check and make sure that the gauges were applied, where they should be, and should have good linearity and hysteresis further down the manufacturing process if it hadn't already gone through pre-cal. And so the blue line is the initial, if you will. The yellow is after moment compensation adjustment. So key things here to note are, one, the reduction in overall error, which is a small amount, but it's a pretty big reduction from pre and post. But also the number of times that the zero balance passes through zero. It went through 2 previously, whereas after a moment, if I can count, 1, 2, 3, 4, and it hovers very close in between there. So what that means now is this load cell has several neutral axes where it's completely insensitive to off-axis loading, which is pretty significant. So again, this is how you can have confidence that if you use one of these low profiles, you're going to get good results in your test. Even if you have, let's say, a long horizontal load string run, you got actuators hanging off of things. Again, sometimes even with support, you still can't quite neutralize. An LP is not going to care in most cases. And we have some customers that really want to know where the neutral axis is, and because we have full traceability during the manufacturing process, we can actually provide a chart similar to the one on the right there that says here, based on the connector, this is where you want to orient those side loads if you can't reduce them. So again, this is something we do on every single low profile, and we make more of these than anybody else in the world. So just a little bit of special that makes these perform better. Next slide. Because we test every unit, you're going to see a couple things on our data sheets where we have a max rated load, but then we also have a max error. And it's not just a theoretical max on the LPs. That's a guaranteed, again, because every unit's gone through moment compensation. And you can see tighter specs for some of these depending on the model too. So, all right, next slide. All right, so temperature compensation. Jacob's done a great job to talk about how temperature affects gauges and things we can do. I think it's important for everyone to leave with an understanding that temperature change around a sensor is going to impact 2 things. It's going to impact the zero balance, right? So that can impact your resulting measurement after you apply load, but it also impacts how much output you get from the sensor. The effect on those can be positive or negative, but it is good to note that it's repeatable. So if you were to take a sensor, run it through an oven, you'd be able to characterize exactly how sensitive it is. But like I mentioned earlier in the presentation, you got to be careful. If it's part of a mechanical assembly, every mechanical joint is going to respond differently, different items in it, right? So it can result in a different applied load. So always best characterize in situ. But how do we address that? Well, as Jacob said, the span adjustment is done from a batch standpoint on the gauges. So we'll basically qualify the batch of strain gauges to within the spec for the particular material they're going on. So whether it's an aluminum unit, whether it's a steel unit, stainless steel, we're going to make sure the batches are properly span tested for that. And then the zero test, this is something we have to do on every single unit. So every load cell that we put together, every time you complete a bridge, you've got to run it through and see exactly how the zero responds to that. So next slide. So as we mentioned, thermal response on output, we'll spec it as a % of reading. So it essentially just affects that slope. We do what we can to batch qualify, to choose the right gauges, depending on the desired temperature range or the material. But as mentioned, when interface proprietary string gauges are used on most of our product there, we don't have to add mod resistors to the bridge to further compensate. So you end up with a fundamentally simpler bridge, less components and to respond to temperature change, but you don't also then have more output. And that's how most of our sensors are 4 millivolt per volt, because we don't have to add things that reduce that signal. So Next slide. Now, as far as temperature comp on 0, again, this is something we do on every unit. We do cold to hot versus some people just doing room to hot. So you end up with a much flatter curve over a wider range. But also, it's good to note that when we do compensate, we don't just adjust and ship, we adjust and verify. Most competitors will put the load cell in, see how much adjustment needs to be done to a bridge, and then ship that unit out, where we run it back through a second time and verify. So again, a little more extra labor, a little more extra cost, but we want to make sure we're delivering the best product we can. And of course, we have full traceability on every unit that goes through the floor. And we can also, of course, do custom ranges, whether it's a customer, a specific comp range in terms of where you want it compensated for, or if it's a matter of doing even span testing. We can potentially do that too and provide actual thermal response to the span. We have some force limits depending on what our ovens can accommodate, of course. But so what does this mean? Well, here's a couple examples, just how tight we can control temperature. Again, our proprietary gauges allow us to really tighten up these specs compared to what you'll find on most force sensors. Our 1100 series, which is our precision model, we're down to 0.0004% reading, or rated output, excuse me, per degree F. So even a 100-degree swing on 1100 series is going to be 4 pounds on a 10,000-pound load cell. So even our 1200 series load cell with 0.0008, again, if it's a 10K load cell, you're talking about an 8-pound error across 100-degree temperature change. So you really don't need to worry about temperature error when it comes to an interface low profile. Why does that matter? Well, oftentimes if it's used somewhere outdoors, especially if you've got the sun working across a test stand, that can make a big difference from early morning to evening or to the middle of the day, excuse me. But again, with an interface load cell, we were able to just control not only the gauge, but the bridge behavior at such a level that it almost pulls that error out completely.
Yeah, I'm glad you mentioned the bridge level, Brian, because the connections that you have in your bridge definitely matter. So if you think about if you had 3 times the wire connecting one leg of the bridge and temperature changed, you could definitely see how the change in resistance of those connecting wires would be 3 times the amount in that leg. So that's very important when considering the assembly of a load cell. You really want to position your gauges and take into account the wire length that you're using to connect your gauges and your bridge. And I think I saw a question here about if I'm operating at constant temperature that is outside the specified compensation range, will the output be as accurate as long as I first zero the output? And that's accurate, yes. So if you go to a temperature and you're able to zero it out, or you know that that's the new zero, from there you'll have accurate readings. The issue is if there's temperature changes and you can't compensate, right? So maybe you're loading as your temperature is changing. That's when temp comp really comes into effect. And like Brian mentioned too, we do plenty of custom range temperature compensations.
I would add to that you're referring primarily to the zero balance, right? So
yes,
you do need to take into account the change to span. So if you are able to apply a known load at that elevated temperature, at least you would know how the span has been adjusted. Now we can give you a calculated value as well if necessary, but if you have the ability to do in situ cal check, it would be very repeatable and consistent. And excellent question that, if you can get your test setup to the elevated temperature range and zero it, now you've removed any temperature effect to zero, right? Because you've already teared that value out essentially, or that shift out. So good question.
Ready? Next slide, please. Alrighty, Brian.
Sorry, I'm muted. While we're talking temp comp, there was another question here, Jacob, and it was temperature compensation appears to assume the entire load cell is at a constant temperature. Is that accurate? Yes, that's fair and accurate. There is temperature compensation performed in a specific area on every load cell in terms of where we can get to it in the manufacturing process after we complete the bridge. So if you were to have two scenarios, one being very localized thermal changes that can impact the load cell's ability to respond properly from a temperature compensation standpoint, or if you have the scenario where you have a thermal gradient being introduced, say, through the load string, that may take time for, again, if the load cell doesn't stabilize thermally, then yes, you could have some less than complete thermal compensation happening from a bridge standpoint. So just for reference, if it's an LP we're talking about, most of our thermal compensation is going to be done for the zero balance, at least behind our label. So pay attention to that. You don't want to have anything hot shooting right at our label. That's not going to allow the thermal comp to work as best as it can. So Jake, were you going to say something?
No, just great question. Yeah.
All right, so the last aspect to keep in mind when we're talking, performance and accuracy is calibration. So, we've talked about designing a good sensor, choosing the right design considerations, building it as accurately as we can, doing some manufacturing tweaks during the process to optimize performance. And the last part of it comes down to calibration. And you can have a spec sheet on a product, and that's how it performs. But in terms of actually getting unit accuracy, unit confidence, in terms of how closely is this measuring 5,000 pounds or 5 kilonewtons, right? The calibration plays a big role. So not only does it obviously verify hysteresis, nonlinearity, all of our specifications that we check for, but the uncertainty around that in terms of the uncertainty of the cal then really plays a big role in, okay, how tight confidence can you have in your test setup? So that's going to come down to the standards that are being used, the traceability on those standards, the stated uncertainty. We're A2LA accredited. We have our scope of accreditation on our website. Tells you the uncertainties there for the different force ranges. We do dead weight cal up to, I believe, 1,100, 1,200 pounds, somewhere in there, Jacob. And then from there, we go to hydraulic reference standard cal, which is what's depicted here, where we're using a couple load cells to track. So in that schematic there, we have a load frame. That top unit would be the DUT, or the unit being calibrated. The unit below that would typically be our calibration standard, where we have very high confidence in that. That goes back to NIST for calibration. Some of our standards in our lab are older than 40 years, believe it or not. So we have binders and binders of history and extreme confidence in those standards. And then depicted under that would be the hydraulic control sensor for the hydraulic frame. So that one would be controlling the actuator to monitor the applied force. So this is a good depiction here. Question just came up: do we sell calibration frames? Yes, we do. We sell essentially what we use every day, and these are cal frames that have to provide 0.04% uncertainty and still do it quickly and efficiently enough to ship out 80,000 sensors a year. So we absolutely do offer a couple of different models, Andrew. We can get you in touch with some information there. So not only does the uncertainty and the standards and what you're using play a role, but there's also what is the specific calibration you're having done. So depending on the sensor, it may come with a tension-only cal, it may come with a compression-only cal, it may come with a universal tension and compression cal. But then also you can keep in mind that if you have a very specific test where you really need ultimate precision, there are options such as asking for specific cal points, where we will actually go and hit that exact point, which is going to drop, linearity, hysteresis. Most of that stuff probably won't matter anymore. Maybe hysteresis, I guess, if you're cycling. But again, you can get better uncertainty through your calibration. We recommend that if you have the ability to calibrate in-house, right, that you calibrate in situ as much as possible, or using fixtures that you would use in your setup. We do have some customers that have us calibrate their unique models using replication of their fixturing, for example. So that's an option. And then we have options such as ASTM 74 cals, which we do on all of our calibration grade sensors. But these will allow multi-point runs and give you lower load limit values, as well as coefficient equations, which, depending on your instrumentation, you can essentially, through software, remove all nonlinearity concerns, right? And really get exactly where that load would be. So, all right, next slide. FAQs.
Yeah,
All
before
right.
we get started with these, we've got a few more questions that came in. So I think This is recorded for those that cannot stay through this, but these are some great questions. So I just want to go through a couple of these. One question, I noticed that my zero reading is drifting every time the load cell experiments temperature cycle, 170 degrees Celsius. Any comment to that?
That would not be typical unless it's in an assembly, which you could have some residual mechanical effects from that. If you have just a sensor sitting there and it's going through temperature cycles and the zero is changing, that's not typical behavior of a healthy load cell. Would you agree, Jacob?
Yes. I also would like to point out, so is it from like 0C to 170C, or is it 170C spread? Because if it's an aluminum load cell, it could be going above the rated
Operating range.
Yeah, operating range. Which basically the aluminum could be tempering and the material properties changing there.
Or gauges separating from the flexure, right? Yeah.
True.
So.
Yeah. Also, I think most of our standard product temperature range is up to 200 degrees. So that might be a time to. Okay, up to 170.
Jaime, let's circle back after this. I'd like to know the model and get some more information, and we'll try to run that to ground. But no, it shouldn't be changing if it's again within the operating range. So, all right, we'll bounce through a couple of these FAQs. I think first one here.
Can I ask you a couple more questions
Oh, sure.
that came in through the chat? When installing a load cell on an actuator rod, does it matter the orientation of the load cell, meaning live end facing actuator body versus live end facing the test article?
I'll take it. Not significantly, but fundamentally, if you have the live end closer to your test article, you're going to have less inertial aspect, especially if it's cycling. So we would recommend that the live end is closest to what you are wanting to test, right? Because if you have that dead end with additional base and the cable, you could have some minor parasitic or inertial aspects impacting what your DOT is seeing versus what the sensor is reporting.
Another question is, how do you overcome crosstalk for multi-channel load cells?
Good question. So you try to optimize through the flexure design. There's going to be limitations, of course, and it kind of comes down to which is your primary axis of measurement. If you're talking an axial torsional cell, for example, and your axis, your axial load is much more important, then we would want to go with one of our 1216 models, which is starts as an LP, an axial load cell, and adds torsional bridges. If you're more concerned with the torsional bridge, then you'd want to start with one of our 5600s, which begins life as a 5400 reaction torque flange sensor, and then we add axial bridges to it. So typically the best thing to do if you're very concerned about crosstalk is to characterize it, right? Do some applied loading, see how it impacts the signal, and then adjust for it in your instrumentation. All right, we're going a bit long, I think, so let's get through some of these FAQs here, Jacob. I appreciate you guys sticking around with us. So which specification is most important when you evaluate load cell performance?
Yeah, I think it depends on the application and what the customer is looking for, right? A good place to start is SEB, but from there it can really depend on how much they are wanting to characterize on their end.
Yeah. So if you need a single specification, SEB is going to give you a good indicator of how accurate the load cell is. All right. How frequently should load cells be calibrated?
That's another good question. I think it depends on the use case again. It's definitely a good idea before a long extended test, or maybe a test where the load cell is going to be subjected to some pretty harsh conditions, to maybe get it calibrated before and after. And that can give you real good confidence for your readings during that test. But besides that, depends on the use case, anywhere from a year to when it needs to be.
Yeah, and we typically recommend tighter intervals as the load cells are newer. They get better with age and more stable with age. I'm talking very, very small amounts. So typically customers would recal at least annual basis until they have good confidence in repeated cals to say that they can be extended. We've done that. Some of our standards, for example, we're able to extend them out a couple of years. So. What environments, applications can load cells be used for? Well, I'll answer that one. I guess pretty much anything. We've got, as mentioned, we've got vacuum rated for space. We've got load cells for oil and gas downhole applications that can be subjected to 30,000 psi with, you know, a couple percent type air influence. So it really just depends. We can accommodate most environments and most applications as long as it's communicated and known up front.
So, Brian, what percent of capacity is the load cell accurate for?
Well, obviously up to calibrated range, 100%. Anything above that, it can start to deviate from that ideal linear output curve. And of course, if you get above 150%, you can start to cause some plastic damage to the bridge and permanent zero shift. So, and now as far as to how low can you go, of course, that gets asked a lot. You know, we can provide certain calibrations that can give you lower load limit values. But a good rule of thumb in general is 10% and up. You should have high confidence in the specified cal values. If you need to go very low, have us calibrate at a low point. You'll have that data point. What are some of the common causes of failure, Jacob?
Yeah, mechanical overload is pretty common, kind of how you mentioned before, especially if there's some forces that are off axis that you weren't expecting. That can cause some combined loading that can lead to premature failure. Another one is like shock loads. Load cells are not really made to withstand shock loads, so it's really good to make sure that you're doing everything you can to avoid those.
Yeah, or if they have side loads that aren't expected, right? Now all of a sudden the strain the bridge is seeing at full scale is a lot worse than maybe expected. So especially if it's high cycles, you've got to be extra careful there. Fatigue type
Absolutely.
testing.
Yeah.
So when should you select overload protection, or when do you need it? Well, you want to answer?
Basically, a lot of the minis have overload protection, and there's a reason for that, right? It's very easy to overload them, even by hand, if there weren't those overload protection features in there. Brian, you have anything there?
Yeah, I mean, as capacity goes down, we typically try to offer it. Just it's necessary. But again, if you've got a test where you're interested in a certain cal range, you know, very tight test range, but then it still needs to see quite a bit of extra mechanical overage, then yeah, overload protection would be good. We should mention too on our low profiles, we didn't touch on it earlier, even though we don't have any EDM features in the shear beam flexures, we can offer compression overload protection by tightly controlling the tolerances between the base and the bottom of the hub on the load cell. So our 1000 series, 1100, 1200, we can offer compression overload protection in the neighborhood of 300 or 400%, I think, through doing that. So again, we have some options there, but typically you can often handle this too with just how do you have it calibrated, right? You can always upsize the load cell capacity, ask for specific cal points, and now in theory, you still have confidence in the test range, but still have a much stronger load cell that can tolerate more mechanical load. All right, this is a good one. So how does the number of bridges improve your load cell performance?
Yeah, so if you have like a second axial bridge, that won't necessarily improve your performance, but it can give you some redundancy and a clean second signal. However, if you have a multi-axis, right, so you have another axis being measured, that can give you a lot more confidence in your readings, knowing how many other off-axis or moment loads are actually being applied.
Good. All right. Do you need to do a system level calibration with your instrumentation? So, all right. So we didn't get into too much detail when you start combining or start talking about different calibration options from a component to a system level standpoint. You've got the calibration of the load cell. You've got the calibration of your instrument. How accurately is it reading millivolt per volt, for example? If you're using TEDs, of course, it really becomes important as you swap out sensors. But typically, we would recommend in-rig system cals if you're concerned about total performance. That's going to take the load cell, the cable, and the instrument all as one system and report it all real time as units in rig in our cal rig. So it really comes down to how much precision do you need, and are you needing to swap out and change from different sensors to different instruments? If things stay paired as a system, then yeah, you can go ahead and get it calibrated that way and you keep that value. But as soon as you change out to a different sensor, there's really not as much value in doing a system level anymore because now it really comes down to the component aspect. All right, what's the FOS of a load cell, Jacob?
Yeah, factor of safety. So that's going to be printed on our spec sheets. It's going to be the ultimate load. It's normally, I think for LPs, I think 300%. And that's when the yield strength comes into play of the flexure of the spring. And if factor of safety is something that your application needs to hit a certain target or something like that, definitely reach out to our applications engineers. And we might want to derate a cell to get a little bit more overhead. That's relatively common. Then Brian, what makes a good load cell material?
Typical answer depends, right? Depends on the capacity,
Oh.
depends on the application, the environment. As long as it's communicated, we can pick the right choice. But I think in general, we talked about good load cell materials should have high stiffness, hardness, act like a good spring. That's the key thing. Otherwise, you're going to run into linearity and hysteresis challenges. So, all right, Jamie, I think you get to wrap this up.
Yeah, we got a lot of good questions there. Again, we'll have this reference material online on our YouTube channel and on our website here in the next day or so. So keep track of that. We'll also be sending you an email with the link. So why Interface? Well, we're a trusted partner. We've been doing this for many, many years. Our engineers, who you've just had a conversation with, design products that are meant to be the best in the world as far as measuring force. And we test and distribute them all over for many industries. We're preferred because of our precision. Accuracy leads all discussion, and we continue to lead the industry in force measurement solutions based on that. So as we noted in the presentation, we design our load cells for precision. We can customize. We have standard products that we can get to you quickly. We also have engineered to order with slight modifications and complete custom solutions for many of our OEM customers. Quality and accuracy are important. Detailed specifications matter. Every product has a detailed specification as well as a drawing online. So use those. If you have any questions, though, reach out to us. And last but not least, if you don't have a copy of our load cell field guide, get a copy. A lot of this technical detail is in this load cell field guide. It's a handy reference. We'll make sure to send out the link in our follow-up communications, but you can also find it online. It's written by engineers. So it's got all the kind of technical detail that we've just talked about. So thank you so much for joining us. We hope that you enjoyed this presentation. We know there was a lot of good information, but if you do have more questions, we will be able to follow up with you as well as just connect with us on the website. We're happy to work with you to get the right solutions in hand or help you through any technical issues. Thanks for joining us today.
Thank you, Jamie. Thank you, Jacob. Thank you all. Really appreciate it.
Thanks everyone for joining.
Thank you. Thank you both.